Good morning, children. Let us solve problems. Today we are going to find determinant, value of the determinant, okay, through different methods. So let us see one of them. Using cofactors of elements of second row, evaluate determinant, that means delta. Alright, so you know that children, last time when we have solved problems, we have seen that we can expand along any row and any column, right? But at that time we were not using the concept of cofactors. So in this problem I am going to use the concept of cofactors. In the last class I have discussed about cofactors minus and cofactor matrix. So let us make use of this. So here they have said that we have to use cofactors of elements of second row. So what I am going to do, second row, let me mark it. Where is my second row? This is my second row. So I have to first write what are my minors, okay. So M21 I am going to write, M22 I am going to write, and M23 I am going to write. Why am I writing this? Then only I will be able to write corresponding cofactors of this. You remember this in the last class. If you don't remember, please refer to the previous video. What do you mean by M21? M21 means you are going to delete that row, that column in which 2 is there. So delete that row. That means if I put a cut here, delete row, that row and that column. So what will happen? What will be remaining, children? 3, 8, 2, 3. Yes, that row, that column. So how much it is? 9 minus 16. So that means minus 7. So here it will be minus 1 raised to 1, 2 plus 1 dot your minor M21. That is nothing but this is position is negative and minus of 7. So this will be 7. Then M22 means second row, second column. So what remains? Second row, second column. So 5, 8, 1, 3. So it is 15 minus 8, that is 7. Now let us write the cofactors. So it is minus 1 raised to 2 plus 2 dot M22, which is already positive. So 7. M23 means what, children? You have to delete second row and third column. Second row, third column. So it will be 5, 3, 1, 2. So 10 minus 3 is 7. But let us decide the position. So it is 2 plus 3 times M23. Which is nothing but, children, negative, right? So it is 7, so it will be minus 7. Now how do you find delta, children? Determinant of delta along second row is nothing but A11 into second row, no? A21 into cofactor of that row plus A22 into cofactor of that row plus A23 into cofactor of that row. Okay, so that will be of that row, no, that element. Okay, this element it's cofactor, this element it's cofactor, this element is cofactor. Now let us substitute. Small a21 is 201. So 2, here I have 0, I have 1. Now look at this one. So 7, a22 minus 7. So it is 14 minus 7. That is 7. So that means your determinant of A or your determinant matrix of whatever is asked in the question, that is delta, is nothing but 7. Okay, now let us move forward. See, I am going to solve more problems of your exercise. I have just taken this in order to just explain you. Okay, now next definition is adjoint of the square matrix A is the transpose of the matrix obtained by replacing elements of the matrix A by its cofactor. What do you mean by this, children? If I am given a matrix A, last class we have learned how to find the cofactors, right? If I remove this part is nothing but my cofactors. So the new definition of adjoint of a square matrix says that if you write a cofactor matrix and if you take transpose of the cofactor matrix, what you get is called as adjoint of the matrix A. Last time we have studied cofactor matrix of element. So this time we are going to learn a new concept, that is adjoint of matrix A. Okay, that was element there. It is now here matrix. So we can see here, children, the minors, the cofactors, the cofactor matrix, all will lead us to this definition of adjoint matrix. Okay, so it means that cofactor matrix you write, take transpose of it, whatever you get is called as nothing but adjoint of that matrix. So here the first row will become first column, second row will become second column, third row will become third column. Is that clear, children? Yes. So this is our adjoint matrix. Okay, now let us solve some important theorem on this. Okay, it says that if A is the square matrix of order n, then A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I, where I is the identity matrix of order n. You know that, children, matrix multiplication is not commutative. Do you remember that? Yes. But in here you can see the commutativity of your matrix A. You can see that when a square matrix A is multiplied by its adjoint, then it becomes commutative, and it also leads us to one formula, that it is nothing but determinant of A times identity matrix. Okay, you all know that, children. If you remember, cofactors, minors, everything, determinants all exist only for square matrix. That's why I've started with the square matrix. So let us simplify this. Okay, let us start with let us prove A into adjoint of A. You know what is A, children? Now it is an n cross n matrix, so it will be too lengthy. So I have taken, for simplification, matrix of order 3. So it will be A11, A12, A13, A21, A22, A23, A31, A32 and A33 into adjoint of A. Adjoint of A, just now we have studied, no, children? Transpose of cofactor matrix. So this time row will be written like this, because it is transpose of the cofactor matrix. A31, A32 and A33. Is that clear, children? So now what I will do, I have to open this, right? So I am going to open this. So how it will be? A11, capital A11 plus A12, capital A22 plus A13, capital A13. Then this row, this column, A21, A11 plus A22. Just see what I am writing. Similarly, third row, first column. This you know how to multiply. Okay. Now first row with second column. Now second. Third row. Third column and first row. Okay. Now children, last time I had told you, children, I have told you one particular property. Just see this. What is this? Yes, this is your value of determinant along first row. This is also value of determinant along second row. This is value of determinant along third row. Yes or no? Just now we have solved a problem and I have seen that an element and its cofactor. Right? An element and its cofactor is nothing but your determinant. But remaining all, just see, it's just a mix match of another entries. An element and some cofactor of some another element is written. And we have seen that in such a situation, the answer is 0. So what will happen? I will get the diagonal elements as determinant of A, and the non-diagonal elements I will be getting as 0. Yes. If I take determinant of A common, this will be 1 0 0 0 1 0 0 0 1. This is nothing but determinant of A into I. This is what you wanted to prove. Similarly, children, the other way around also, if I do, you can get determinant of A into I. So I am not proving it. So it's understood. A into adjoint of A is adjoint of A into A. is equal to determinant of A into I. Just remember this property, okay? We are going to use this. Even though it's a theorem, we are going to use it in some situations. Now the last topic which we are going to learn today is singular matrix and non-singular matrix. Okay, when is a singular matrix and when do you say it's a non-singular matrix? So a square matrix is said to be singular if determinant of A is 0. Otherwise, it is said to be a non-singular matrix. Just see this. Now, if I calculate the determinant, it is 12 minus 12, which is 0. If you calculate the determinant of this, it is 12 minus 12, which is 0. Right? So, when your determinant of a matrix is 0, it is called as a singular matrix. And when the determinant of a matrix is non-zero, then it is called as a non-singular matrix. Okay, now these are all things we are learning in order to find a shortcut for finding inverse of a matrix. We know that we used to find inverse of a matrix by doing elementary row transformation or column transformation. So we are learning all these minors or cofactors or adjoint or singular matrix, non-singular matrix. These all will lead us to method of how to find inverse of a matrix. So let us wait for that topic.